different sort of particles that we commonly come across here in nuclear chemistry. And for example, the alpha particle, which is sometimes written a couple of different ways. And that represents our alpha particle. It's basically a helium nucleus, is why helium is used a lot. Also the beta particle, which is also written a couple of different ways. We also have gamma, which is just pure energy. Other common things that we come across are protons, which also have a couple of different sort of symbols that are used. Also neutrons as well. And positrons, which have sort of the same deal as our beta particles, but it's basically kind of like a positive electron. So these sort of different particles are really important, especially if we're going to talk about sort of balancing equations and so forth. Understanding these guys. So I don't think we got too far into it. So let us continue. So I think this is where we left off. We're going to talk about balancing nuclear equations, and balancing nuclear equations is like super hard. Not really. It's really just adding. So when we balance a nuclear equation, there's really kind of two things that need to be balanced, a little bit different than a traditional equation. And that is pretty much when you add up all the mass numbers, which a reminder is the number that is up on top is the mass number. The atomic number is the number that's on the bottom. Mass number is obviously our protons plus neutrons, right? Atomic number is our protons here. And when we add up all the mass numbers on the left-hand side here, they need to equal all the mass numbers that you add up here on the right-hand side. So here we have 235 and 1, which gives you like a 236 there on the right-hand side, or left-hand side. On the right-hand side, we got 138 plus 96, and we would also multiply 2 times 1 there on top, and that would give us 2 more, which would give us 236 there on the right-hand side. On the other thing that needs to be balanced is the atomic number. So the number of protons there. And it's the same deal on the left-hand side is what we're looking for on the bottom. So in this particular example here, that is a 92. And adding up all of the atomic numbers on the right-hand side gives us 92 as well. So to have a balanced nuclear equation, that's pretty much all you need to do is make sure all the mass numbers on the left equals the right, and all the atomic numbers on the left equals the ones on the right. So how would something like this go? Well, one way is something could be missing from this equation. So for example, if we took out, say, this guy right here, and we weren't sure, you know, what that was, we can look back at this and basically add up the bottom number, as that is going to be what's going to tell us what element or particle is missing. So on the left-hand side, we have 92. If we add up everybody but the guy box, that's 55, and 0 gives us a 55. So basically, if we subtract those two numbers, that is going to give us a 37, which is the missing atomic number that we see there. We would then go to the periodic table, which is our other good friend when we're doing these type of equations, and we would look up number 37 there, and we would see the symbol RB, and that is, again, how we get to that guy that would be in the missing box. To finish out the top number, we would do the same thing. So before we had 236. Without the middle guy there, we basically had 138 plus 2, which is, again, from here, you got to multiply those two together, gives us a $1.40 there. Once again, if we subtract the 140 from the 236, that is going to leave us the 96, where our missing sort of mass number would come from. So that is one way these sort of problems are, something sort of missing in the equation, and really the good approach is to go with the atomic number, because in most cases it will match somebody on the periodic table. It is potentially possible that the missing thing is one of those particles, so maybe a hydrogen, which would still match, an alpha particle, which would probably still match as well. But you know, you could have a neutron, you could have some other type of particle that's missing. But probably 9 times out of 10, you could go to the periodic table and find sort of the element that's missing. And then you want to finish out by figuring out your missing mass number. Now, the other way is you'll sometimes just be given things sort of in words, if you will, and they'll say, hey, this guy goes through alpha decay or beta decay or something like that. So they'll sometimes say, hey, it goes through alpha decay or any of those other particles. And what that essentially means is, in terms of the arrow, that is where it will end up, will be on the product side. So if anything goes through any type of decay, they will typically tell you what type of decay, like alpha decay, beta decay, positron emission, something like that. Those particles will end up on the right-hand side. Your original guy will end up on the left-hand side, and then you could proceed to figure out what the new isotope would be on the other side. A couple other words. So anything that is going through decay, anything that is emitted, those particles always end up on the product side. Anything that is bombarded, anything like an electron capture, those particles end up on the reactant side. So those are the common sort of verbiage that you sometimes see in these problems. Bombarded, electron capture, that's going to put that particle on the left-hand side. The reactant side, anything that goes through some type of decay, emits some type of particle, that particle ends up on the product side of the arrow. What we also see here is sort of the hallmark of a nuclear reaction, which is there is no conservation of elements. So unlike in a chemical reaction, where we balance the equation by putting coefficients in front, because we do have conservation of the elements, because those guys only involve electrons. Here, what we are really changing is everybody in the nucleus, so protons to neutrons, neutrons to protons. And as we change the number of protons, we are changing what the element is. So there is no conservation sort of elements in nuclear chemistry. And it is the proton or the atomic number, right, that determines what element you're talking about. As the number of protons changes, so does the element as well. Any questions on that there? All right, so why don't you give this a go. PO212 decays by alpha emission. Write the balanced nuclear equation for this decay process. And again, if you have a periodic table, it's probably going to be super helpful. If you have one, you might want to pull it out. Help you for some of these things. Take a look at this. So first off, we are starting with 212 PO here. 212 is the mass number. We could go to the periodic table to fill in our atomic number. If you do, it looks like it's an 84 there. It is going to decay by alpha emission. So again, that alpha emission means that on the right-hand side, our product side, I should have my alpha particle, which again, you could write this way or this way, whichever one you prefer, is all good. And that means we are going to really be missing one more thing here to sort of complete out the equation. Once again, I personally will start with the atomic number, because that's going to help me go to the periodic table and find what I need. I obviously have 84 on the left-hand side. I got 2 on the other side. That means if I subtract that, my missing atomic number is 82. And once again, I could simply go to the periodic table and find number 82, which is our good friend lead. And to truly finish it out here, we're going to finish our mass number. So once again, on the left-hand side, I got 212. Right-hand side, I got 4. And if I subtract that, that gives me a mass number of 208. If I could write the 8 there, 208. And that means that this would be our balanced equation. Once again, if we look at the mass number on the left, there's a grand total of 212. On the right, 212. Left atomic number 84, and our atomic number on the right there 84 as well. questions on that? So not too bad, a little bit of adding in a periodic table, and it should be good, hopefully. All right. Hopefully they agree. So they do, that's good. So let's talk a little bit about the differences. We sort of alluded to some of the differences here between the chemical process and a nuclear process. As we talked about earlier, really chemical reactions, it's all about breaking bonds and making new bonds, which is all electron driven. So we really don't touch anything in the nucleus. And again, that's why when we balance regular chemical equations, we do have that conservation of the elements on each side. If you start with 4 carbons, you should end with 4 carbons and so forth. But in nuclear reactions, like I said before, it's really all about sort of those particles within the nucleus that are changing. And obviously it is the most important one out of those is the protons, as the number of protons changes. So again, does our element. So that is why we take the mass number, atomic number approach to balancing, where essentially we're keeping track of all the particles that kind of came off from the nucleus and all that as well. Sometimes you'll also hear a word in nuclear chemistry, sometimes referred to as nucleon. And that's basically the protons and the neutrons, basically the particles within the nucleus. And sometimes they'll be called isotopes, guys, or they'll be called nuclide as well. So those are some terminologies you sometimes see. So what is happening here as we kind of go through this and look at sort of what happens when we do go through, for example, a beta decay. So in this case, our beta decay here is 0 minus 1. We actually will increase the atomic number there by 1, because 7 minus or plus minus 1 is 6, and 14 on top. So we actually decrease the neutrons by 1 and increase the number of protons by 1. That's a neutrino. We're not going to get too much into that. You don't have to worry about it. It's got 0 and 0 type of thing in terms of its mass and atomic number. But really what's happening in a beta decay is one of the neutrons within the nucleus gets converted into a proton, and the result of that is it emits off a beta particle, which is why the emission occurs here. So we're transforming a neutron into a proton. Ultimately, what changes is really just the atomic number. In reality, the mass number does change, but it ends up going back to basically where it started. So if we just do a step by step, for example, we look at 14,6 carbon, we are taking a neutron out, which means technically our mass number would then go to 13,6 carbon when we subtract our neutron, right? Then we form a proton, right? So we add a proton, which takes our mass number back up to 14 and our atomic number to 7 in this particular case. And so that is how come really the mass number doesn't change overall, but you know, there is a process that does change. It actually has 1 less neutron, but it's compensated by gaining 1 more proton. So overall it doesn't change, but there is that sort of real change that's sort of happening as that process occurs. When we go through a positron decay, which again, like I mentioned before, has pretty much the same symbols that we see for a beta decay, but they definitely will emphasize the plus there. And I think I might have mentioned it last time. Sometimes they will write these things just like that sometimes. And again, if you see the negative, it's the beta. You see obviously the positive is the positron. And if you just see beta written like that, it's probably fairly safe to assume that it is the beta particle that the person probably was talking about. In the case of a positron decay, we're taking actually a proton and converting it into a neutron. The result of that is our positive positron gets off. And overall, the same thing sort of happens here. The mass number overall doesn't change, but our atomic number does go down by 1. And again, if you just followed it, not 100% correct, sort of step by step, we take out our proton, which takes us down to 10 and 5 carbon. And then we add our neutron in, which takes us back up to 11 and 5. So again, overall it doesn't change, but we do have that conversion of the proton to the neutron. Any questions on that there? A couple other ones that are common. This is our electron capture. And again, you could see the capture part of it means that an electron is actually on the reactant side in that case. And in this case, the proton and the electron will come together basically and form a neutron. And once again, here are mass numbers not going to change, even though it goes from proton to neutron. So it compensates for each other. And overall, we do see a drop in the atomic number on the right hand side. The biggest change obviously occurs with our alpha particle here. We have a 4 and a 2 that happens in terms of the mass number, decreases by 4 the mass number, and also increases by 2 there, our atomic number. Now, fission is the process where we really break apart a nucleus, our nuclide, into 2 new nucleuses, and also usually accompanies some neutrons being released and also energy being released. And this could be a spontaneous process where, like in this case here, this californium basically breaks off into these 2 guys, releases some neutrons and some energy. It can also happen by what is known as sort of bombarding a nucleus. So you can shoot a particle at it like a neutron, and that's going to make it very unhappy, and then it's going to become something that's unstable, and then we'll actually go through fission and split off into 2 new nucleuses. As we'll talk about later, not always going to be the same 2 guys, and there's different ones that are formed every time along the way, but you can't necessarily predict per se what will be formed. Here's just a table, and you have a similar one in your book of all the reactions that we just talked about there. So why don't you try this one? Write the nuclear equation for the positron emission of potassium 40. Okay, let's take a look. So potassium 40, obviously, if you're not sure, that 40 is the mass number here. And that is another very common way isotopes are written, symbol dash a number. And that is usually the mass number. We know it definitely is the mass number because we can go to the periodic table and we see that for potassium, the atomic number is 19. So clearly that was not the atomic number. We are going to do a positron emission. So once again, emission means that particle is going to be on the product side, and that's a positron. So your choice, you do the beta or the E, whatever one you like to do, but it is the positive version of it. That means, if I'm doing some good math here, that's like an 18, I think we need there to get us to 19 on both sides. Going back to the periodic table, number 18 is our good friend Argon. On the left-hand side, we have 40 for the mass number up on top, 0 on the right, which means that's a 40 on that side, and we should be good at that point. Any questions on that one there? All right. All right, so why don't you finish up here, do these 4, write some balanced nuclear equations for each of these. Alpha emission, uranium-238, beta emission, neon 24, positron, nitrogen 13, and electron capture, beryllium 7. Let's see how you're doing. So we'll start with the first one. That's uranium-238. So that's a good place to start. Uranium, again, the 238 being our mass number, which would go top left. We could go to periodic table there and find the atomic number, which looks like 92. Alpha emission, once again, means our alpha particle will find itself over here on the product side. Looking at our atomic number on the bottom, I got 92 on the left and 2 on the right, which means my missing atomic number should be 90. I will go to the periodic table and I see number 90 is TH. Going to the top there, 238 on the left and 4 on the right means that to get us to 238, we would need 234 there. And that should be our balanced equation. And once again, you could use helium, obviously, for 2 helium there instead of the alpha symbol. Any questions on that one there? Going to neon 24. Once again, being our Mass number, our atomic number from the periodic table is 10. In this case, we have the beta emission, which would be something like this. In this case, our missing atomic number actually needs to go one higher because that's -1. So that's actually an 11 that we need there. 11 and -1 gives us 10 on the right and 10 on the left. Number 11 would be our sodium here. And overall, the mass number will still remain at 24. Looking at the next one, which is nitrogen 13. Once again, going to the periodic table, we find nitrogen's number 7. In this case, it's a positron emission, which is very similar to what we have above, except that is +1. And in this case, that means that actually 6 would be our missing number there. And number 6 there would be carbon, and 13 up on top. Yeah. Any question on those 3 there? Lastly here, beryllium 7. Beryllium is number 4 on the periodic table. This is an electron capture, so capture means it actually will be on the reactant side. So our electron should be over there. Looking at our atomic number on the bottom there, we just need to add them, so that's 4, and -1 is a 3, which should be lithium from the periodic table. Up on top should be 7. Any questions on how to balance nuclear equations? Not too bad. Okay. Excuse me. Okay, so next thing we're going to talk about then is stability. And one common way that we sort of measure stability of nuclides is to do what is sometimes referred to as the N to Z ratio. The N meaning, excuse me, the N meaning neutrons, the Z meaning really the atomic number or the number of protons. So really our neutron to proton ratio here. And it is a measure of stability. There is a certain ratio depending on sort of the atomic number of a nucleus or element, the proper stable neutron to proton ratio. Now, if we do end up with perhaps something that has a ratio that is maybe too high or too low from this sort of stable part, it will really go through sort of decay to try to bring itself to a more stable ratio of neutrons to protons. So the first thing that could happen is you could do the sort of neutron to proton ratio, and it can be too high. And if it's too high, what will end up happening is it will go through a decay process where neutrons are converted to protons, and basically will go through a beta decay. So if you find your ratio is too high, it will go through a beta decay. Now, if you calculate your neutron to proton ratio and it is too low off of sort of a stable situation, we will actually get protons converted to neutrons, and that will basically bring up our ratio closer to a more stable situation. And it will go through one of two situations. It will go through either a positron emission or an electron capture. So go through one of those two. It can do alpha decay, but it's not as efficient. So for us, if it is a ratio that is too low, you should be doing one of these decay processes here in the box, either a positron emission or an electron capture. Now you may say to yourself, is there a difference in terms of what you get? So let's take a look at our beryllium 7 that we just did there a second ago. We did our beryllium 7. And again, we went with an electron capture in this case. And we ended up with 3, 7, and lithium. Now, if we did a positron emission, starting with our same guy that we looked at the last one there, positron emission would look something like this. where we would end up with a 7,3 and lithium. So either a positron emission or an electron capture will yield you basically the same result there. So that's why, again, you have sort of a choice. You could go through either one. They both will end up with the same guy at the end there. Any questions on that there? All right, so how do we know if it's sort of the ratio is too high or too low? Let's take a look at this graph here, which will help us understand that. This is what is sometimes referred to in some books as the valley of stability. Some books also call it the belt of stability. If you like belts better, go with the belt. And that is this yellowish, if you will, sort of guy. And that is our sort of valley or belt of stability. Now, if your atomic number goes from 1 through 20, a stable ratio is a ratio of 1. If your atomic number is somewhere between 20 and 40, you're looking at a stable ratio of 1.25. If you're 40 to 80, you're looking at a ratio of 1.5. And pretty much anything above 84-ish there is not going to be stable. So it will, don't have to really worry about it. Now, to make it easier for us personally in this class, we're going to use these as a hard cutoff. So either the ratio is 1 or it's too high or too low. Yeah, or the ratio is 1.25 or it's too high or too low. I will tell you that, as you can see here, one ends at 20, right? One begins at 20, and obviously one ends at 40, and one begins at 40. So there is sort of a grayish area between those two where they sort of transition from one to the next. And sometimes books will go, well, it's okay because it's sort of in that grayish area. So just for us in this class, we'll just keep it a hard cutoff. Either, again, it is that number, or again, it's too high or too low. But be aware in the book, there's sort of a grayish area as you sort of transition between the different cutoffs, where sometimes they'll say it's still, you know, okay, and that type of thing. Now, it will go through either, as we saw there, our beta emission or positron emission or electron capture. Will that perfectly fix it? And the answer is sometimes it will and sometimes it will not. But what you will see, for example, is if you are like this side of the valley, when it goes through that emission, your new guy should be moving down towards it. Or if you're a little bit below it, after it goes through its emission process or decay process, it should move itself up towards it a little bit closer, a little better of a ratio. In these type of problems, you don't need to keep going until you hit the perfect ratio. You just need to do like one of the decay processes. But again, what you should see is it's just kind of move you in the sort of correct direction. It may, in certain cases, be perfect, but it may not always be exactly perfect after you do one of them. Any questions on that there? So why don't you try one? Predict the kind of radioactive decay that magnesium-22 will undergo, and why don't you write the reaction? Let's take a look. So obviously here we're going to look for our neutron to proton ratio. So once again, magnesium-22, and we could get from the periodic table there that it is number 12. The number of neutrons would be found by taking the mass number minus the atomic number, and that is going to give us a grand total of 10. Obviously, the atomic number is the number of protons, so our N to Z ratio here would be 10 divided by 12. Want to get us a 0.833, I think. 0.833. The atomic number here is 12, which means an acceptable ratio for this guy would be a ratio of 1. And in this case, we are too high or too low. We are too low. So we find ourselves sort of on this side of the valley. So this is then going to go through one of two things. It could go through a positron emission or an electron capture in this case. So let's take a look at what those reactions would look like. We'll do our 22 magnesium and 12. We'll do our positron emission. And again, you can use the E or the beta symbol there. That means we will end up with an 11, which is sodium. And up on top would be 22. Now, if you did the electron capture, you will end up with the same guy, not the same equation, obviously. So electron capture would look like this. And again, 12 minus 1 would give us the 11 and 22 sodium here. Question on that one there. Now, yeah, either one's okay in this case. You also write them both, so it will go through either one. So on a question or something like that, you can lay up either one. Should be fine. Yeah. Because the main thing is they both give you obviously the same outcome, and that's really what we're looking at. Because now we can look at what it's now become, right? Which is sodium 22, which means for our sodium 22, it has 22 minus 11, which would be number of neutrons. 22 minus 11 is 11, which means its ratio would now be 11 divided by 11, which would be 1. So in this particular case, just this one process, either one of them, actually brought us back up to our stability that we need. We're actually way back here, but back up to our stable part by doing this one decay. And again, it doesn't always come out that way that you hit the perfect ratio, but again, it should move you, towards the perfect sort of ratio. Question on that? All right, let's try another one here. Krypton 85, is it stable or radioactive? If it is radioactive, again, predict the mode, and why don't you also write the balance equation for it? And Krypton, in case you don't have a periodic table, is lucky number 36. Look, so we have Krypton here. And 85, and once again, from the periodic table, we can get our 36. That is going to allow us to get our neutrons, which would once again be our mass number minus our atomic number there. Want to give us a 49. That means our N to Z ratio would be 49 divided by a 36 in this case. Going to get us a ratio of 1.36. In this particular case, we're looking at 36 in terms of the atomic number, which means it falls between the 20 to 40 range, which a good ratio, I believe, should be 1.25 in this case. That means in this case, we are too high here. So here's our belt. We're on this side of it. We need to come down to the belt of stability. So because we're too high, it should go through a beta decay here. And let's see what happens when we do that. We'll take our 85, 36. Once again, decay will put our particle on the product side. We will need to go to 37 in this case. 37 and minus 1 is 36 on the bottom. And we will still have 85 up there up on top. Number 37 there on the periodic table is RB. And this would be our mode of decay that would occur. Now, if we look at RB and see if we did any better, let's see. So that's going to be number of neutrons will be 85 minus 37. So that's going to give us 85 minus 37, gives us a 48, which then takes 48 divided by 37. Gets us down to about a 1.3. So again, here it didn't get us perfect, but it is moving us, in the sort of the right direction, closer to that belt of stability. Any questions on that? Yeah. You would, in these type of problems, you just do the first decay process. Unless it's a specific question that says keep going until, keep doing the process until you hit something that's perfectly stable. But in most cases, it's just a one process and you should be done. Other questions? Okay, so this is one way that we could look at stability, which is, again, the neutron to proton ratio. There are other ways to predict stability. And let's talk about some other, ways that we look at stability here. Besides the neutron to proton ratio, the number of protons and neutrons, what I mean by that is it even, odd number of protons and neutrons. So most stable nuclei, the most stable sort of arrangement you could have is if you end up with an even number of protons and an even number of neutrons. There's like 100 and whatever it says there, 57, I think it says, of stable nuclei that has even and even. The next sort of best situation is actually even number of protons, odd number of neutrons, and there's about 33 or so of those guys, or actually 53. And the next would be even neutrons, odd number of protons, there's about 50. Really the worst situation is when you sort of end up with a guy that's got odd number of neutrons and protons. There's only about 5 stable guys that have that sort of arrangement. So, you know, just really quickly looking at something, if you see like even and even protons and neutrons, that's probably going to be a fairly stable guy. If you see odd and odd, probably going to be not so stable as the situation there. Also, if the total number of nucleons add up to magic numbers, once again, nucleons are really our particles in the nucleus, which are basically our protons and neutrons, which is basically our mass number, right? It's sort of the same idea as sort of, you know, there's like noble gas configuration. Everybody's a little bit stable. Everybody's trying to get to the noble gas configuration. So the most stable situation is when either the neutrons or the protons are 2, 8, 20, 28, 50, 82, and your mega ball number, their Powerball number is 126. We can go play those later. If the neutron is 126. So those are just found to be sort of stable nuclei when we have either neutron or protons that are basically these guys are this. So 2 good ways probably to look at stability really is if you can do the neutron to proton ratio, that's a good way to look at it. And also, like I said, even and even. We'll look at something a little bit later on in this chapter, which is known as binding energy. That's another way that you could look at stability of a nuclei based on its binding energy per nucleon as well. Let's talk a little bit about decay series. A decay series is one in which a radioactive nuclei will basically continue to kind of go through the decay process until it sort of hits something that is sort of stable. As we talked about before, what we start with is sometimes referred to as the parent, and what we end with is sort of the daughter nuclide as you go through that. So a big series of these steps, sort of one right after the other, is what is referred to as a decay series. And again, it will continue until basically, you know, you hit something that is relatively positive or relatively stable in that situation. There's a couple ways you could do it, especially if it involves alpha and beta decays. One way you can do it is just to write the balanced nuclear equations, where basically your product will become your reactant in the next step, and you kind of do that process all the way through. You also can, if you just are maybe curious of what you get at the end of the process, and it's all sort of alpha and beta decays. For every beta or alpha decay, you subtract 4 from the mass number and 2 from the atomic number. And for every beta decay, you then add 1 more to the atomic number for each of those. And you can just kind of figure out at the end. So let's just say we had uranium-238 there. And I'll just make it up. We'll just say it went through alpha, beta decay sort of process. We'll do a very short decay process here of only 3. And there's, again, 2 ways we could do this. We could just do it like we did before there, where, let's kind of clear it off here. We could just write our equations. So we would do our first one, which would be uranium-238. And again, uranium from the periodic table is 92. First process would be it would go through that beta decay or alpha decay. And once again, our missing atomic number would be 90, which would go to periodic table and find that it is TH. On top would be 234. The next process that would happen would be that what we just formed, as is a decay series, will continue to decay and also go through a alpha, which would then give us on the bottom 90 on the left, 2 on the right. Our missing atomic number would be 88 in this case. 88 on the periodic table there is Ra. Up on top, we have 234 and 4 on the right, which means our missing guy would be 230. And that would take care of the second sort of decay process. Continuing on, this guy would then become our reactant, which in my made up one here will then go through a beta decay, and that would be 0 minus 1, which would take us back to 89 and a 230. Once again, go in the periodic table, a little actinide there would be it. So you could do just like nuclear equations and balancing them, where in a decay series, you take your product that becomes a reactant, product becomes a reactant, and you could go through each of the steps. Now, for example, if we were just perhaps interested in, where we end up in this very short process here, we could start with our uranium 238 and 92, and it went through 2 alpha decays, which means I should subtract 4 and 4 from the top and 2 and 2 from the bottom. And it went through 1 beta decay, which means I should then add 1 back. So taking care of my top here, I would have 238 minus 4 gets me to my 230. 92 minus 2 is 90, minus 2 more is 88, plus 1 is 89. And then obviously I could go to the periodic table and find what it is. So that's sort of a shortcut if it's alpha and beta decays. If you just want to kind of figure out what you get at the very end of a 10-step decay process, and you don't want to write each one individually, you can kind of shorthand it and sort of figure out where you will end up. Any questions on that there? And clear, usually decay processes or series are relatively long, as we can see here. Here's actually our uranium 238, and it actually will go through kind of 2 processes. It will typically stay through this run, and then sometimes it will go this route, and then sometimes it will go this route. The end result, though, is whichever route it takes, it will eventually get down to lead 206 there, which is sort of a stable nuclei. So we'll continue through this entire process here until it hits that stable nuclei. So again, in a situation like this, if you were given a problem where it's like, hey, it went through this whole decay pattern here, you might not want to write out each equation, right? Which you could do, but you just maybe want to know what you get at the end. Again, you could do the -4s, -2s, and +1s, and sort of figure out at the end what you should end up with. Any questions on decay series? So let's talk a little bit about radioactive decay and kinetics. All radioactive decay will follow first order kinetics. So if you remember kinetics, vaguely, basically all radioactive decay will follow first order kinetics. And first order kinetics basically has a couple of important equations. First off, I'll call it K. This is what is referred to in nuclear chemistry as the decay constant. And sometimes nuclear chemists will use lambda for that. In regular kinetics, we call this the rate constant. Same deal. By the way, that's lowercase k, not capital K. And the rate constant, or decay constant for first order kinetics, always has basically 1 over seconds or 1 over some unit of time. is the units that's associated with it. And again, it could be 1/seconds, 1/minutes, 1/hours, 1/days, years, whatever it may be. But those are the units that are typically associate with the decay constant or the rate constant for first order kinetics. There's what is referred to as the integrated rate law, which is the natural log of A is equal to the natural log of A naught minus KT. And this is your final, could be concentration, could be grams in the case of nuclear chemistry, could be percentage, could be a rate of radioactive decay. The A naught is your initial, and obviously the K here is our decay constant, and T here is time. Yeah, so that is time in that case. As you can see on the bottom here, nuclear chemists like to use their own symbols sometimes. So they sometimes will use like the natural log of N is equal to the natural log of N naught minus lambda T. And these are for nuclei, but it's the same thing as concentration. And that again is the decay constant, and that is time. So sometimes you'll see some different symbols, but they basically represent the same thing. It is also a half-life. The half-life is the time it takes for half of whatever you started with basically to go away. And that is the natural log of 2 divided by the decay constant or the rate constant. And if you take the natural log of 2 on your calculator, that is 0.693. So that is where that number comes from, and the decay constant. Now, a lot of times in these sort of problems, you'll need to use both of these equations together. So sometimes they will give you the half-life, and you will need to use that a lot of times to figure out the rate constant or decay constant, and then you need to use the integrated rate law there to figure out, you know, what you're looking for, whether it be concentration or time or whatever it may be. So these are common graphs that we see for first order kinetics. And like I said, this is sometimes how nuclear chemists like to use this formula. This is the first order plot. As you might remember, you can rearrange this equation where the natural log of A is equal to minus KT plus the natural log of A naught, and that is Y is equal to MX plus B. It will give you basically a straight line plot where on the Y is the natural log of the concentration, and on the X is time. And if you take the slope, it is equal to minus the decay constant or the rate constant in this particular equation here. Any questions on that? What's that? Yeah, so lambda is one that sometimes nuclear chemists will use to also be the rate constant or decay constant. So sometimes you'll see the N and the lambda used. I think a lot of books now will just go with the A's, like kind of like the same one that you see for rate constant, but some older books and some other places would use sort of the more nuclear chemist sort of nomenclature. It's sort of the same thing. If you remember kinetics, maybe when you did it in the first part, 200A, a lot of times what we use in these guys are concentrations, but it really doesn't have to be concentrations. You can use really any units you want for A and A naught, as long as they're the same units. So you could use, like I said, concentration, which is very rarely used in nuclear chemistry, but things like grams, milligrams are used a lot on both sides. You could also use things like radioactive decay or rates of radioactive decay, like counts per minute or something like that on each side. You could even, like I said, use percentages on both sides. So although we kind of look at this as concentration, in the application of nuclear chemistry, we could really use any unit as long as they're the same on both sides. So you don't have to like convert it to concentration or anything like that. You could go right in with grams and grams or milligrams and milligrams into those equations. Questions on that there? So let's talk a little bit about half-lives. Obviously, it varies depending on the substance that we're looking at. Some half-lives can be very long. So like uranium-235 there, That's like 4.5 times 10 to the 9 years for half of it to go away. I don't think any of us will be here for one half-life on that. Carbon 14 there is 5730 years, but some are very, very quick. Like radon 220 is like 55.6 seconds. So every minute, basically half of it goes away. So it's really quick. And then some are, even quicker here as well. Clearly, as we'll talk about, if you're going to use obviously some type of radioactive isotope for any type of medical, say, purposes, you would obviously want a very small half-life, right? So the follow-up appointment is not way in the future. So usually quick half-lives, maybe minutes, maybe hours is used. But again, depending on what the substance is, it may be a fairly long sort of half-life. All right, so what we will do is we'll take a break right now, I think,